Hello, everybody. I am going to finish discussing the chapter on the heart. So let me go ahead and share my screen. So we left off talking about the circulation going to the heart, called the coronary circulation. So that's back here. And what I want to do is just continue with this chapter on the heart. And we get to talk about the heartbeat next. So the heartbeat obviously is when all of the muscle cells of the atria and the ventricles contract in a coordinated manner. And what happens is all of the muscle cells around the atria contract, and then a split second later, all of the cells around the ventricles contract. Okay, so there are two types of cardiac muscle cells involved. There are contractile cells, so muscle cells that actually contract and get shorter. And then there are cells of the conducting system. Most of what makes up the cardiac muscle are the contractile cells, the cells that actually get shorter and do the contractions. And when they get shorter, what they do is they squeeze the chambers of the heart and they propel the blood to the different areas of the body. But there are some cells, a few cells in the heart that are the conducting cells. And what those do is they actually create their own impulse. So you don't have to get any kind of a signal from your brain to your heart, cause it to contract. You actually have cells in the heart that can start their own conduction signal, can start their own action potential. And so there are these calcium voltage gated channels that stay open longer than they do in skeletal muscle contractions. So when we talked about nerves and them activating the skeletal muscles, we said that the skeletal muscle, when it gets activated by a nerve, calcium flows into the skeletal muscle, and that causes this whole big contraction. Well, we have those same kind of channels in cardiac muscle, and we have the same sodium and potassium channels that we saw in the nervous system. So what happens is those cells depolarize because there's an influx of sodium, and then they repolarize due to an efflux of potassium. Basically, it's all the same things that happen in the nervous system when one neuron conducts action potential to another neuron, but this happens right within the cardiac muscle cells. So differences between cardiac and skeletal muscle, one major difference is that it's a longer duration of contraction. Whereas skeletal muscles contraction gets brought on very quickly and it's over very quickly as well. Cardiac muscles contract for a much longer period of time. So it's a little bit slower to get them to contract, but they're contracting on a regular basis for a much longer period of time. And unlike skeletal muscle, cardiac muscle cannot respond to another stimulus until the membrane repolarizes. So in skeletal muscle, we said there's this thing called tetanus that happens, right? Where you contract a muscle, and as it's starting to relax, you stimulate it again, and it contracts with more force. And before it completely relaxes, you stimulate it again, and it contracts with more force. And you keep going until you reach a plateau called tetanus, where the muscle is completely contracted and essentially locked up, and it can't relax anymore. Well, with cardiac muscle, that can't happen. You can cause the cardiac muscle to contract, and there won't be another stimulus in the cardiac muscle until it completely relaxes. Okay, so there's no summation, there's no actual tetanus that happens. So what this happens is that what these things allow for, first of all, is that the cardiac muscles can contract without any kind of input from other systems, right? You don't need a signal coming from your brain. You don't need hormones being secreted from different glands or anything like that. The cardiac muscle just automatically contracts. And there are cells embedded in that cardiac muscle that establish the rate of contraction. Primarily, the sinoatrial node, the SA node, and the atrioventricular node. And I'll show you on the diagram in a minute where those are. And so what happens is the sinoatrial node contracts, and then it distributes that signal through conducting cells. And then the AV node contracts, and it distributes its signal through some conducting cells. So I'm actually going to go to this diagram. I'll just zoom in a little bit. So the SA node, here's our heart. The SA node are a group of cells right at the top of the right atrium. That's considered the pacemaker of the entire heart. This is going to set the pace for contraction. When the SA node creates an impulse, not getting an impulse from anywhere else, it's creating it from within. That impulse travels, and you can see where it travels with the arrows and the purple kind of shading. It travels through both atria, so both through the right and the left atria at the same time, causing the muscle cells of both the right and the left atria to contract. Then what happens is the AV node sends a signal. The AV node, atrioventricular, is between the atrium and the ventricle. So the AV node contracts and it sends its signal down the septum, the interventricular septum, so the septum between both ventricles. Those are called bundle branches. Excuse me. Those are called bundle branches. It sends a signal down bundle branches and then back up along the outside of both ventricles. Those are called the Purkinje fibers. And in doing so, it causes the muscles around both ventricles to contract. So all that happens is the SA node contracts, causing the atria to contract. Split second later, the AV node contracts, sends its signal down the middle of the heart, back up the sides, and the ventricles completely contract. And this whole thing, from start to finish, time zero, until the ventricles contract, is only about 225 milliseconds. That's 225 thousandths of a second. So this is happening, 4 times a second, which is pretty fast. So you need to know both of those nodes and the bundle branches, the Purkinje fibers, the different fibers that conduct those. Sorry about that. All right. So this just goes into the words that I just said. The SA node is where the contraction starts, and it travels through the AV node. If there are problems with the pacemaker, if the SA node is causing contraction slow, right, too slow, less than 60 beats per minute, that's called bradycardia. And tachycardia is the opposite of that. It's where the rate is set too high, so your heart is beating too fast. And sometimes when abnormal cells generate action potentials so quickly that they override the SA or AV nodes, that's called an ectopic pacemaker. So in almost all these cases, what's going to happen is a pacemaker will get inserted, a mechanical pacemaker that triggers those cells to contract at a certain rate. The next part of the chapter goes into one of the ways that doctors read or diagnose heart problems, and that's through the use of an EKG, which is called an electrocardiogram. So sometimes it's abbreviated ECG, sometimes EKG. This is a recording of the electrical events in the heart. Okay. And what we have is a wave that looks like this red wave on the bottom. So kind of a small bump, a large spike, and another small bump. That first small bump is called the P wave. The spike is called the QRS complex. And that third bump there is called the T wave. Now, what these waves represent is electrical activity of the actual cardiac muscle cells, right? So when you see a bump, when you see a line going up, it means there's an increase in electrical activity. This first little bump, this P wave, which is kind of small, correlates with the electrical activity of the cells surrounding both atria, right? So this is the depolarization or the spreading of the signal through the muscle cells of the atria. The QRS complex, which is much bigger, correlates with the depolarization of the muscle cells surrounding both ventricles. It's much bigger because the ventricles have to push blood out of the heart to either the lungs or the systems of the body, right? So you have to have a much stronger signal and a much stronger contraction. Remember that the atria are only pushing blood down to the ventricles. It doesn't have to be very strong. The ventricles have to contract with a lot of force. The T wave, this third little bump here, correlates with the repolarization of the ventricle, the muscles around the ventricles. So when those muscles around the ventricles relax completely, that gives you the second little bump. So you get a bump when you see depolarization and then a bump when you see repolarization. The repolarization of the atria happens at the exact same time as the depolarization of the ventricles. In other words, there should be a fourth bump, but it's in here, it's in this QRS complex, so you'll never see it. And so you need to know what the three bumps are, what the three waves are, and what they correlate with. Now, this is a normal looking EKG. Sometimes abnormal EKGs, you could see if there's, a shorter distance between the P and the QRS complex, then, there's something going on with the timing of the signals. Sometimes you get multiple QRS complexes before you get a P complex. Again, these are all ways to diagnose different heart issues. Okay. So we go from talking about that to talking about the cardiac cycle. The cardiac cycle is the period between the start of one heartbeat and the start of the next. So from the beginning of one heartbeat, not just till it ends, but until the next heartbeat begins. It includes alternating periods of contraction and relaxation. Contraction in the heart is called systole, and relaxation is called diastole. So when the chambers relax, when the muscles relax, that's called diastole, the chambers are filling with blood. So the heart relaxes, blood can pour back into the heart. Then once those chambers are somewhat full, the muscle around the chambers contract. That's called systole. And that ejects blood, right? That pushes blood out of the heart. So the cardiac cycle starts with the atria contracting, right? The atria contract. That's called atrial systole. What happens is that's going to push blood down into the ventricles. And in doing so, it opens those AV valves. The next thing that happens is the atria relax, right? That's atrial diastole. The atria relax, the AV valves slam shut, right? And the volume in the ventricles does not change at this point. So the blood has already rushed into the ventricles, right? Basically what happens is atrial systole push the blood into the ventricle. Then the atria relax, the amount of blood in the ventricles doesn't change. It's already there, it's already full. Then what happens is ventricular systole, right? The ventricles contract and the blood is ejected from the ventricles into the artery. And then ventricular diastole, right? That's where the ventricles relax and the semilunar valves slap shut. And that allows blood to start flowing back into the atria and all the way through into some of the ventricles. Okay, so again, I'm going to kind of zoom in on this a little bit. So start of the cardiac cycle, atrial systole. So blood is here in the atria. The atria contract and they push blood down into both ventricles. And then atrial systole ends and atrial diastole begins. So atria can relax. Then, and at that point, you can see that the blood has filled up both ventricles. Then ventricular systole starts, right? And that pushes the blood into both the aorta and the pulmonary arteries. Then what happens is ventricular diastole. The ventricles relax. They've gone from squeezing here to being relaxed. And blood can flow all the way in, not even just stopping at the atria, but it can flow into the ventricles. All right. So we know that, when doctors listen to your heart with a stethoscope, they listen for certain sounds. They listen for what's called the lub-dub sounds. There's a first heart sound and a second heart sound. The first one's called lub, or S1 for sound one. The second one is dub, or S2 for sound two. So normally you hear that lub-dub, 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 right? What they correlate with is not the movement of blood, because the movement of blood just sounds like water rushing, right? It's just, you wouldn't hear any kind of thumping noises. The thumping noises that you hear, the thumping noises that a doctor hears, have to do with the valves closing. So that first heart sound has to do with the AV valves closing. So that first heart sound indicates that blood has moved from the atria into the ventricles, and those AV valves slap shut. That produces lub. The second sound is produced when the semilunar valves close. So once the blood is moved into the ventricles contract. They push blood into the arteries, and the blood, once the blood is in the arteries, the semilunar valves stop shut. That produces DUP. That produces S2. And so here you can see just a correlation with where the blood is, right? And producing the first sound in the heart, the second sound. So the AV valves closing produces lub. Then the semilunar valves closing produces DUP. Then we get into heart dynamics. Heart dynamics have to do with the forces that are created when the heart beats and how much blood is, leaving the heart, getting through the heart to different areas of the body. And there's two things that doctors are interested in, or two kind of calculations. One is stroke volume and one is cardiac output. Stroke volume is how much volume of blood leaves the ventricle in one heartbeat. So when the heart beats, when it squeezes, how much blood is leaving the ventricle? It's not all the blood in your body. It's not even all the blood in your heart, right? Not every drop of blood is going to leave your heart every time your heart beats. Cardiac output is how much blood leaves your left ventricle in 1 minute, right? So how much blood are you getting to your body in one full minute? So it's stroke volume is how much is leaving in one beat. Cardiac output takes that into account, plus how many heartbeats you have in a minute. So it's the total amount of blood that's leaving your heart in 1 minute. And that's a really good indicator of blood flow through the tissues, whether or not you're getting, significant or adequate blood flow through the tissues. So cardiac output equals your stroke volume times your heart rate, how many times your heartbeats per minute. Increases in heart rate or stroke volume can increase cardiac output up to as much as 30 liters per minute. So probably obvious that, if you increase your heart rate, if you have more heartbeats per second, per minute, that your cardiac output will increase. Right? That makes sense. But what if you increase stroke volume? And a lot of times that's what you're doing if you're, training by doing things like running or cycling or doing things that are increasing your blood flow. What you're doing is you're getting your heart stronger, and it's increasing how much blood is pumped every time your heart beats. And that's also going to allow you to get more oxygen to different parts of your body, right? It's going to increase your cardiac output, how much blood is leaving your heart per minute. And that will actually ensure that you're getting more oxygen to your tissues, which you need when you're exercising. So blood volume reflexes are a direct relationship between the volume of blood returning to the heart and the volume of blood ejected during the next contraction. So another way that you can increase your cardiac output is to make sure that your veins are working efficiently enough to return a large volume of blood to your heart. So what you want is that the more blood gets returned to your heart, the more blood can be ejected during the next contraction. So there are two heart reflexes that respond to change of blood volume. One adjusts your heart rate and one adjusts stroke volume. So as you start returning more and more blood to your heart is automatically adjusting how many times it beats per minute and how much output there is, right? Just based on there being an increase in blood coming back to the heart. And you have a couple of these. You have an atrial reflex, which is called the Bainbridge reflex, where if you increase the amount of blood that returns to your heart, it causes the atria to stretch. And what that does is it increases your sympathetic activity, which causes your SA nodes to depolarize faster, which makes you increase your heart rate. So as you're returning more blood volume to the heart, your heart rate's going to increase beating because now you got to get that blood back out to your body. And the Frank-Starling principle indicates that the stroke volume depends on venous return and filling time. So the faster the heart rate, the shorter the filling time. If you return blood back to your heart and you wait 5 seconds before the heart beats, that's going to be a lot different than if you return blood back to your heart beats after 1 second. It's not going to be filled nearly as much after 1 second as it will be after 5 seconds. There is a lot of autonomic innervation of the heart. So we talked about contractile cells. Your heart has cells embedded in it that cause the heart to beat, right? And those are the pacemaker cells of the SA node. They establish your basic heart rate. They depolarize on their own without any kind of signal coming from anywhere. But they can be modified by your autonomic nervous system. You can speed up or slow down that heart rate. And that's what this is talking about. So you can't cause the heart rate to happen. You can't cause those cells to contract. But you do have both parasympathetic and sympathetic nerve fibers going from your brain to your SA node, right? Parasympathetic nerve is mainly your vagus nerve, which is cranial nerve number 10. That's one coming off of your brain, which slows down your heart rate. Parasympathetic is going to slow down your heart rate. There are also sympathetic fibers, and there are numerous ones that extend from the cervical and the upper thoracic ganglia that will cause you to speed up your heart rate. So the interesting thing about this is that the SA node on its own would create a much faster heart rate than what you have, and it's the innervation by the vagus nerve that slows that down. So average heart rate's about 60 beats per minute. I think without your vagus nerve being normal or being active the way it should be, your SA node would set the pace of your heart much faster than 60 beats per minute. So they affect the SA node pretty much. The parasympathetic pathway is going to slow your heart rate. Sympathetic pathway is going to speed up your heart rate. How is this all coordinated? Well, there's the cardiac centers in your medulla oblongata, and that's going to either speed up or slow down your heart. And a lot of that is due to changes in blood pressure, how much CO2 is present. There are changes monitored by baroreceptors, so how much your pressure is. So not only how much hydrogen is there, how much H2 is there, but how much pressure is there. And then there's information from the receptors of the brain via cranial nerve 9 and 10. So, again, 10 is that vagus nerve. There are also hormonal effects on the heart. So in addition to those direct connections from your brain, we learned that if your brain perceives a threat, there's a direct connection between your brain and your adrenal gland, and it will cause your adrenal medulla to release norepinephrine and epinephrine, which will increase your heart rate. That's called adrenaline, right? That's what we normally call adrenaline. That'll increase your heart rate. There's also the connection between thyroid hormones and your heart rate, right? Your thyroid hormones control your metabolism. So if your thyroid hormones are being secreted at higher levels, you're going to increase your heart rate. Try to break down your nutrients. So, and there. So that is the cardiac chapter, or the heart, I should say the heart chapter. What we will do is we will meet on Wednesday. We plan on meeting on Wednesday at 9:30 at our regular time. And we will start going over the chapter on the blood vessels, I'm sorry. And at that point, I want to discuss the section of the heart. So go ahead and look at the demo that I have of the heart dissection. That'll be the next lab that we'll do over the next week. We'll dissect the heart, and that'll be our lab for that week. So if anybody has any questions, please feel free to email me, and I will see you guys on Wednesday.